Okay, so the topic now is coloring. I gave you some examples in the very first lecture of this course for coloring vertices of a graph, and there'll be more examples for coloring the edges. Let's not do examples now, but just let me give you the two definitions that are needed. So this x is a chi, right? The chromatic number is the smallest k such that G has a proper k vertex coloring, which is an assignment of colors to all the vertices so that adjacent vertices are are colored differently. Okay? So if you like, formally a map from the vertex set to some set of colors so that adjacent vertices have distinct different images. So then there's the edge chromatic number, which is the same for coloring the edges, and conveniently we have a comprehensive notion of being adjacent. So adjacent edges must receive different colors, and two edges are adjacent if they're like that. Okay? So this is the chromatic number, that's the edge chromatic number, or sometimes also the chromatic index. Okay. And there are, as always, two aspects to studying such invariance or anything else. Much as we did for matching, one is to, given a graph, find an optimal coloring or a good coloring that uses few colors on the vertices or few colors on the edges, and that's relevant for applications. So in these various applications, usually there's a theorem that tells us, or sometimes there's a theorem that tells us how many colors we need to color, for example, the edges. But to find such a coloring for the concrete application so that it can then be used is still an interesting problem. So an algorithmic problem to find good colorings. And for vertex coloring, this is famously or notoriously hard. That's for the computer scientists amongst you, that's an NP hard problem to decide whether a given graph has chromatic number at most k for any given k, even 3. I mean, not 2. Right. We'll get there later. So let me start with the example that I gave you earlier with a map coloring problem. And the map coloring problem now translates to the, let me call it the 4-color theorem. Every planar graph G has a 4-vertex coloring. Right, that's the famous 4-color theorem. So every map as a corollary of this modeling of maps by graphs, every map can be colored, the countries in every map can be colored with 4 colors at most, so that adjacent countries, those sharing a boundary, receive different colors and can therefore be distinguished on the map. Right, so this problem was posed as early as 1852. And then it wasn't too well known for a while, and then Cayley, whom you may know from your algebra course, proposed it to the London Math Society or Royal Society or something, Royal Society probably in those days. And then a year, that was in 1878. And a year later, Alfred Kemp. So maybe Kemper, I don't know, his name. So this was Cayley, Kemp. Don't know how to pronounce him. In the UK, people say Kemp, usually, as far as I know. But he was British, so maybe it's Kemp, maybe it's Kemper, but his first name is Alfred. So, anyway, so he proposed a proof, and we're going to see the essence of that proof in a moment. Unfortunately, the proof wasn't quite correct, and it took a little while until 1880, when Percy Haywood. Right, now this is H-E-A, and he's not pronounced Hewood, he's Haywood, right? So Haywood in 1880, turned the false proof, Kemp's false four-color theorem proof, into a correct five-color theorem proof that every planar graph has a 5-vertex coloring, a proper 5-vertex coloring. So of course I mean a proper here. And we shall see that proof in a moment. So what about the 4-color theorem? That had its first proof advanced in 1977, and this was by Ken Appel, and Wolfgang Haken. So he's an American mathematician. He was a German mathematician working in the UK, in the US. I think he's got only one. Okay, Wolfgang Haken. And they published a computer-aided proof where they used a computer back in 1977, right, to check thousands of so-called unavoidable configurations, whatever that means. It was a finite task for the computer to do, and they generated all these configurations, and then the computer checked these things, whether they could be four-colored or not. And there's been a bit of discussion about whether that constituted a proof or not. Much of that discussion is about computer proofs in general. And I don't want to comment much on that now, because there's a lot of development there right now. I'm not an expert in it, but systems are now being developed that can check human-made proofs if they're written up in a sort of slightly formal way, but not too formally, and even systems that can come up with proofs. But this is developing so fast at the moment that I'm not qualified to tell you a lot about it. In those days, the question was, well, is that a proof of, can we trust a computer to check all these cases? Now, in reality, the question was more like, can we trust Appel and Haken? So people came up with configurations that they hadn't checked. And that was, I think, only after, I can't remember whether that initially happened or at some point there was a poor master's student who was tasked with checking that proof. And so the way I know the story, unfortunately, I can't give you any references. The way I know the story is that this poor master's student gave up at some point and said, sorry, I couldn't do that. And people kept finding configurations that hadn't featured in the published proof. And each time, Apple and Harkin responded by saying, oh yeah, that's right, yeah, let's add it. And now it's complete. And then somebody else came and said, oh, well, what about this one? Oh yeah, let's add that one too. And now it's complete. So that went on for a bit. And then so this was 1878. This was 1879. This was, no, that's not right. That's not right, is it? What did I say? Yeah, the false proof was 79, that's right. Yeah. So this was 1977. And then in 1997, Neil Robertson, Dan Sanders, Paul Seymour, and Robin Thomas developed those computer methods a little further, and they found a different setup or an extended setup where they had to check far fewer configurations, and the written paper is only 20-odd pages, and I read it at the time, and it appeared to be correct. The computer program they used has been reprogrammed independently by other people and found the same result. So that, I think, is pretty reliable now and can count as a proof, and the four-color theorem can count as a theorem. Right. So let me show you the five-color theorem. And two proofs of that. And then after the first proof, I will ask you, doesn't that prove the four-color theorem? So I'll put you in Kep's shoes, and so maybe you can keep an eye on that as I speak now. So the proof idea is to delete a vertex, apply induction, so five-color the rest, and then put the vertex back and hope that it doesn't see too many colors. If it sees only four colors, we can color it with the fifth color. So it certainly helps if this vertex that we delete doesn't have too many neighbors. So let's delete a vertex V of degree. How small can we get in a planar graph? They can't all have degree 172. Or can they? Well, if the average degree was 6 or greater, then the epsilon of that graph will be 3 or greater, right? Half that. And then this graph would have 3n edges, where n is the number of vertices. But planar graphs don't have 3n edges, they have 3n minus 6 edges at most. So we can find a vertex of degree at most 5. We can't have min degree at least 6. Okay, call that V. Color G minus V by induction with at most 5 colors. Okay, then the neighbors of V in this coloring of G minus V use all the colors, because if they don't, we can color V with the color to which it isn't adjacent. So they use all the colors which I now name 1, 2, 3, 4, 5 to avoid having to go back and forth with colored chalk. Right, and now I enumerated these in a cyclic fashion. That's highly suggestive and also highly dangerous, because what does it mean, a cyclic fashion? Well, this is a plane. Yes, it's a planar graph, so we can have an embedding in the plane. And from last chapter, you ought to be able to come up with a cyclic ordering of these neighbors in the plane. So you make a tiny little disk around V that sees only straight line segments there, and then you use your, what have you, e to the I theta formula for increasing angles, and then you come up with a cyclic ordering of these. I don't want to do that now. We had enough elementary topology in the last chapter. So I'm ordering these cyclically now, but I'm warning you that there is a little bit of technicality in doing that. And now, let's look at the neighbors of 1. Maybe it has a neighbor called 3. Maybe that has a neighbor called 1, colored 1. Maybe that has some neighbors colored 3, and 1, and so on. And let's just consider the component containing this vertex here. That consists of vertices colored 1 and 3. And this component, I claim, also contains this vertex. Because if it didn't, we could switch colors in this component of this 1, 3 graph, H1, 3, and then this would be colored 3 after the switch, and this could be colored 1. So if we can't do that, then we'll reach 3 in this component, so this vertex in this component. Then let's just remember one path from here to there in this component, so as not to clutter the board too much. And now let's do the same for 2 and 4. So we have 2, 4, 2, 4, 2, and 4. And now these two ought to meet for topological reasons. So the white cycle here separates this vertex from that vertex in the plane. That takes a little bit of proving, but only of this elementary type that we had last chapter. So there can't be a path from this vertex to that vertex that avoids these edges and the vertices colored 1 and 3. In particular, there can't be a path in G or in G minus V that uses only the vertices colored 2 and 4. And that's a contradiction. And the end of that proof. So, question? We never looked at that. So let's redo the same proof for the 4-color theorem. And this must have been something like what Kemp did. I didn't read up if it can be read. I don't know what exactly it did. But let's try and prove the 4-color theorem in this same way. So we find a vertex of degree at most 5. Then we color the rest by induction, and we look at how many colors are used in the neighborhood. If there are fewer than 4 colors used, we can color V with a 4th color. So there are 4 colors used. 1, 2, 3, 4. And this has one of those 4 colors too. So we can do the same argument. Do you dare object? No. Homework. Okay, it's an exercise. Say what exactly goes wrong. Maybe it's too easy. I didn't find it easy. When I was a student, I didn't find it easy. I thought I was really puzzled. Anyway, so second proof, which is embarrassingly simple. So second proof of the five-color theorem. Same start. We find a vertex of degree at most 5. And then we notice that some 2 of its neighbors must be non-adjacent, because if they were all adjacent, then we'd have a K5, which we can't have in a planar graph. Now, you might object that we're using Euler's formula here. And indeed, it would be nice if we didn't have to. And I think later in this course, I think later in this course we shall, in fact, see a proof that doesn't use Euler's formula of the five-color theorem. But in finding this vertex of degree at most 5, we already use Euler's formula because we used the planar graphs have at most 3 and minus 6 edges. So nothing more is used than we did already. So there are non-adjacent vertices adjacent to V, call them U and V. And now do something really, really simple. Contract this path. That gives you a smaller graph. Still a planar graph, because contraction preserves planarity. Either because it does, and you see that in the plane, or by Kuratowski's theorem. Right, so we have a smaller planar graph. We can color that with 5 colors. The contracted vertex gets some color, red. Then color G minus V in this exactly the same way, giving U and V this color red. And that's fine because they're non-adjacent. But now we have a coloring of G minus V that doesn't use all 5 colors in the neighborhood of V. And we can color V with the missing color. End of proof. Isn't that brilliant? This is correct, I think. But I only learned that proof a year ago. So apparently this was known to some people, and I asked around, and I found some people who knew it, amongst them Paul Seymour and Carsten Thomason. And, but nobody wanted to own up to it. Nobody wanted to say, yeah, I found that proof. I don't know, because it's so simple. And I was able to trace it back to Douglas Woodall, who used it in his lecture notes in 1972. He was one of my PhD examiners 100 years ago. So the other was Nash Williams. So apparently, and I wrote him, he's still around, and I wrote him, and he said, I don't know whether that was my proof, but I certainly have it in my lecture notes in those days, and nobody hinted at anything earlier than that. So I'm attributing this now, for want of any more information, to Douglas Woodall. Very, very nice, simple proof. Questions? No, it's easy. Okay. Then there's a 3-color theorem, which I'm only going to mention. Well, maybe 513 if G doesn't contain a triangle and it's planar, then we can make do with 3 colors. That's Grutsch's theorem, 1959. Okay, there's a short proof due to Carsten Thomason somewhere. It's not that much prettier than the original only it's a lot shorter, but neither of them is pretty. Okay. Right, so let's consider the second of our two topics. The first was come up with algorithms that actually do find a good vertex or edge coloring for a given graph. The second theoretical one was relate or prove some theorems about these chromatic numbers, and the theorems that we prove tend to have the form of relating an invariant to other invariants. So we'll be relating it to the number of edges, to the min degree, and to the max degree, and a little later also to the girth. Okay, so now the question will be vertex coloring. Can we prove some theorems saying so and so many colors are enough? Like four-color theorem, right? But now for arbitrary graphs. Maybe with some conditions depending on these. Okay, so the aim is find and prove upper bounds on chi in terms of those other invariants. And here's a very, very simple observation. If we take an optimal coloring, so color classes 1 to all the way up to k, if it's an optimal coloring, then there must be edges between all color classes, otherwise we can merge them into one. So this means that G has at least, well, how many? Chromatic number of G choose 2, K choose 2 edges. Right? I mean, very, very, very crudely, one between every two classes. And you can so if you fix the number of, if you call K, if you call the chromatic number K, then you can show that G has at least K choose 2 edges. So conversely, if the chromatic number forces, an assumed chromatic number forces up the number of edges, then you can conversely bound the chromatic number by a function of the number of edges. So this function turns out to be just sort of translating that, right? So that turns out to be half plus root of 2 number of edges plus a quarter. Don't learn that formula. Just remember this obvious thing. Okay, but I'll be referring to this back to this later, so I want to have it on the board. Okay, so now let's look at something slightly less trivial. Let's color the vertices greedily. Maybe you have heard of the greedy algorithm in other contexts. It's a general method. It's not anything precisely defined. So for vertex coloring, it means just enumerate all the vertices and start coloring with the smallest available color, where smallest refers to the set of colors being some set of natural numbers like 1 to k, right? So we color this one. If there's an edge here, we can't color this one. If there's an edge here, but not here, we color this one, and so on. So always look at the next vertex, look at the back edges. Those rule out certain colors because the neighbors backwards have already been colored. And then take the smallest available color and give it that color. And it's called greedy because you just look what's ahead of you and say, yeah, I take that, take that, take that. Right? You take the first color, you look at just the next vertex, you don't plan ahead, you don't make any big theories, you just look at the next vertex and say, what can I do with you? That's why it's called the greedy algorithm. Okay. Now, that gives us a trivial proof, well, it gives us a proof of the fact that the chromatic number is at most delta of G plus 1, right? So how many edges can you send backwards? Well, at most big delta, at most max degree edges. And then you need one more color to color this vertex. So that's trivial, a trivial corollary of that. And the first slightly non-trivial observation is that we haven't only colored the vertices greedily given the enumeration, we also greedily picked an enumeration, which is any, just take it. But we can now try to think a little bit about it, and what would be a good way of listing the vertices? Well, we want these, every vertex to send few edges back, right? So if we have V1, V2, and so on, and this is Vi, in GI, the subgraph induced by the vertices V1 to Vi, we want Vi to have small degree. So why not try to give it the minimum degree of this subgraph? Well, it's not an obviously clever idea, but one can work a little to show it is a clever idea. And so how do we, well, suppose we have no, let me just make a definition first. The coloring number of G, something like the chromatic number, and that is the smallest k such that for a suitable vertex enumeration, every vertex has fewer than k earlier neighbors. Right, so amongst all the possible vertex enumerations, let's choose in the abstract. I'm not telling you how to find that, but let's sort of suppose we have almighty powers to find the right vertex enumeration that minimizes, that for which that optimizes this strategy. Right. The smallest k such that the greedy algorithm performed on this particular vertex enumeration uses fewer than k, uses the most k colors. That's the coloring number of G. And now we've just shown that the chromatic number is at most the coloring number precisely by this algorithm. Okay, so how would we find this enumeration? I'll show you an attempt, and then later I'll show you that this in fact does it. So the attempt is to say, let's start at the back. Let the last vertex be one of smallest degree in the entire graph. Well, that's one instance of this where Gi is G. Right? We want this to have min degree in its Gi, and its Gi is G. And then, having done that for this, we do the same for this. So we give this the min degree in this subgraph. And in general, we choose Vi so that it has min degree in Gi. So okay, so that's one particular strategy to order all the vertices, to choose this enumeration. And so we have shown that the coloring number, which is the smallest k so that any of these works, which is certainly no bigger than the k for which this particular choice of enumeration works. This is at most, well, the maximum of all these back degrees plus 1. So that's the maximum of all delta of H, any subgraph of G plus 1. I'm being pretty sloppy here, so I'm maximizing over all the subgraphs. We only need to maximize over those that we're considering here, but for good measure, let's just throw that in. That makes the maximum bigger because we're considering more H's, and the coloring number is certainly at most the maximum of all the min degrees of all the subgraphs of G, plus 1. It's in fact, at most, the max of all the min degrees of the subgraphs of this form Gi plus 1. Okay, and now a simple but important observation is that the coloring number of G is certainly no smaller than the coloring number of any of those H's. Right? If you take a subgraph, it doesn't need more colors. And also, you can do the same induced ordering on the subgraph and so on. So this is at least the coloring number of every H in there. Now, the coloring number of any H in there is at least its own min degree plus 1 because it has a last vertex in its optimal enumeration, and the degree of that vertex is something. And so, in fact, we get an equals there. Okay. So this in particular shows that our choice of an enumeration by going backwards and always choosing a vertex of min degree of what's left is in fact an optimal choice. Yeah. So that much about the coloring number and the greedy algorithm. And one corollary is so that's for 523. If the chromatic number of G is K, say, this is just my name for the chromatic number, then then there exists an H, a subgraph of G, whose min degree is at least k minus 1. If all subgraphs had min degree at most k minus 2 or even less, then we could add 1 to all these min degrees and get a coloring with at most k minus 1 colors for G. So that's a corollary just of this. And the new thing is that we can find such an H even with chromatic number K as well. And the proof of that is simpler than going through all this. What's the proof? Easy. Take G itself. It has chromatic number K. Delete vertices, keeping the chromatic number K as long as you can. And at some point, we still have chromatic number K. We have a subgraph H. Still chromatic number K. But as soon as we delete any further vertex, the chromatic number drops to K minus 1. Now, I claim that this subgraph has min degree at least k minus 1. Why? If it had degree at most k minus 2, we would pick a vertex of degree at most k minus 2, delete it. Then the chromatic number goes down to k minus 1. Then we put the vertex back. It has only k minus 2 neighbors. And we can color it with one of the first k minus 1 colors as well. Yeah, so such graphs that are k-chromatic. K-chromatic means having chromatic number exactly k. That are minimal with respect to vertex deletion with this property are called vertex or critically k-chromatic. So we often say minimal, which usually refers to edge deletion. And when we want to refer to vertex deletion, we usually say critical. So there are minimally 5 connected graphs. Delete any edge and you lose 5 connectivity. There are critically 5 connected graphs. Delete any vertex and you lose 5 connectivity. Now, same for chromatic number. A critically 5 chromatic graph is one that needs 5 colors. It can also be colored with 5 colors, but as soon as you delete any vertex, you can color with fewer colors. Okay. Right, and now the only substantial theorem of the day. That's Brooks's theorem. But before I show you what it says, can anyone think of an example where this bound is in fact attained, or might it be a suboptimal bound? Might we have a smaller upper bound for all graphs there? Can you think of a graph that does need delta plus 1 colors for a vertex coloring? Yeah, it's always difficult to ask it that way. When I tell you the answer, you say, yeah, of course. So the 2 examples that you can think of are complete graphs. Right, they have degree, a Kn has max degree n minus 1, but it needs n colors. And odd cycles. So odd cycles need 3 colors, but their max degree is 2. Okay, so those are counterexamples. And the question now is, can we improve the trivial bound, the trivial upper bound, maybe for graphs other than those 2? Okay, the answer is yes. I'm going to show you a theorem that does that. And it has before I reveal the statement, let me tell you about the sweat conservation law in mathematics. So there are conservation laws in physics, like energy and mass and what have you. There's also one in mathematics, and it's the conservation of sweat. So when you have a difficult theorem that is difficult for good reasons, not because you have to go through lots of pedestrian little cases, that is difficult for a good reason, then it saves you sweat elsewhere. It's applicable, and it crops up here and there unexpectedly, and so on. And Brooks's theorem is my prime example for the sweat conservation law in mathematics. So this is 524. 24, that's Brooks. 1947 or something. 1941. And it says that the chromatic number of G, which we assume to be connected, it doesn't make much of a difference, but it makes it easier to state, is in fact at most delta. So you save 1. 1. Unless G is complete or an odd cycle. Okay, so that's Brooks's theorem. Let me prove that to you. We do induction on the order of G again. Pick a vertex. Delete it. And I claim that we can delete, that we can color the remaining graph H with delta of G colors. So I want to use the symbol delta now for delta of G, not delta of H. Right? Delta is now fixed for this proof to mean delta of this G that is given. But I have to persuade you that this is in fact true. So when we have V and we delete it, for a start, the rest might not be connected. Okay, that's not so bad, right? So if we can color all the components with delta colors, then the union of these colorings is a coloring of H minus V, of G minus V, H. Okay? What else could go wrong? Well, it could happen if we want to apply the induction hypothesis now to these components, not to G minus V itself, but to these components. It might happen that we're not allowed to because they're a odd cycle or a complete graph. Yeah, but then if this is a Kn, then its delta is going to be smaller than the delta of G, than our delta, because V sends an edge there, because G was connected, so V sends an edge to every component. And this vertex here has an incident edge going back to V, and it has the usual incident edges from a Kn. So its degree in the Kn is smaller than its degree in G, one smaller. So we can use the trivial upper bound, this one here, for the Kn. So we can color the Kn with n colors, with its delta plus 1 colors, but its delta plus 1 is our delta. So that's fine. And similarly, if we have an odd cycle here, then the same applies. So its delta is 2, which is strictly smaller than our delta, because some vertex in this odd cycle sends an edge to V. So we can also, again, use its own delta plus 1 set of colors, i.e. 3. And that still gives us a delta, our delta coloring for this odd cycle. Okay, so those are the two cases we had to be aware of, and they're fine. So we can now assume that all the components can be colored by induction with our delta colors. In fact, with their delta colors, but we're not assuming anything about that because we don't know anything about that. So these components might have the same big delta than our G. So let's just stick with this delta. Notice that I'm not assuming now that H is connected. Right? We're done with applying the induction hypothesis. So we applied this to the components of H, but all I'm using from now on is that H is colorable with delta colors. Okay. So let's make some observations. First observation is the coloring that I'm going to use is now going to be called C, but it's important that C is any coloring. We're not picking a particular one and then using its properties at some stage, but we're doing everything from now on for any coloring C using at most delta colors of H. The first observation is, let me write it in text, it's easier, that C uses all delta colors on neighbors of V, on these vertices here. Right? We're only coloring G minus V, but I can still ask which colors are used on these vertices here, the neighbors of V. And the answer is all of them are going to be used, because if they weren't, we could color V with a missing color. Okay, second observation is that so let me use yellow to indicate the number of the colors. The second observation is that the component for every I not equal to j, and these are colors, the component Cij of Hij, Hij is, as before in the 5-color theorem, Hij is the subgraph of H using colors I and J only. Spanned subgraph of H. Induced subgraph of H. And the component that contains okay, Vi. Okay, since we have one that C uses all the colors on the neighbors, I may as well enumerate these neighbors by their colors. So we have V1, V2, V3, V4, and so on. And this is V delta. So the component of Hij that contains Vi contains Vj2. So same as before. If we started at V1, say, I is 1 and J is 3, for example, or yeah, whatever. So we took I, J, I, J, and so on. If we didn't get to Vj, we could just switch colors in this component. And then we'd get a proper coloring of H, where this vertex no longer uses color I, but color J, same as Vj. But that would contradict 1. And remember, 1 is true for all colorings. Right? So we'll get to Vj at some point. Three, Cij for all Ij, Cij is a path. Just a path. It can't be less than a path. It has to contain Vi and it has to contain Vj. But it's only a path. Let's prove that. So, okay, here's my I. Let this be J. So we have I, j, I, j, running out of space. Okay, this is j. I, j. This is my path. I want to show that the entire component Cij of the graph Hij is just this path. So let's check whether Vi has any other neighbors in Hij than this one on this path, which exists in our, just pick a path in this component here. Right. Can it have another neighbor here? That would be color J as well. Well, not really, because what's the degree of Vi? In G, it's at most delta. But this edge is not in H, so in H, it's at most delta plus delta minus 1. If it had another J neighbor, then the neighbors of this Vi would use only delta minus 2 colors. But then we could recolor Vi with a different color. I is one of those two missing, but we have another. So we could recolor Vi, and then we'd get a contradiction to 1. Bingo. So Vi itself doesn't have any other neighbors. So for that same reason, Vj doesn't have any other neighbors in Hij. But maybe some other vertex does. So let's look at the first vertex. The first vertex along this path that has a neighbor outside that path in Hij. Yeah, so then this vertex has 3 identically colored neighbors. It has degree anything up to delta, but we're not using 2 colors because 3 neighbors all use the same color J in this case. Okay, so we're only using delta minus 2 colors. It has 1 color. I. It has 1 color, and we can switch it to another color. So where's the contradiction now? It's a contradiction to 2, that the component using Vi and Vj in any coloring includes the other one. But it doesn't. Once we've switched this color, just change the color of this one vertex, this component gets stuck here. So that path up to there, not including this vertex, would be the entire component. Okay. And then we just need one more observation. And that is for all I, j, and k, distinct, Cij and Cik meet only in Vi. So the vertices of Cij, which is a path from Vi to Vj, are all colored I and j. This is a path from Vi to Vk. All these vertices are colored I and k. So potentially they have an intersection anywhere where they have an I vertex. And the claim is they only meet at Vi. Well, they must meet at Vi because they're both paths from Vi to some other V, j and Vk. And the claim is that's the only intersection. Yeah, but same argument. So let's now start at I again. And let's look at the path from I to k, Vi to Vk, this path here. And suppose that it meets this path from Vi to Vj in a vertex that is not Vi. Yeah, but then, how many neighbors does this vertex have? Well, up to delta, we can't say anything more, but it has two neighbors colored j, and it has two neighbors colored k. Right, this is an inner vertex of both paths. So again, we're saving two colors. We're only using delta minus two colors at most on the neighborhood of this vertex, so we can recolor it. And now we get another contradiction. Well, again, contradiction to 2. So when this is recolored, then following this path here, we get stuck. And that is a component of Hij that doesn't include Vj. Right, and that's all I'm going to use to wrap up the proof now. Okay. I just deleted what I wanted to use later, but never mind. I'll just redraw that picture. We have V, V1, V1 has a non-neighbor amongst the neighbors of V. Oh, not V1. There exists a non-edge amongst the neighbors of V. The neighborhood of V cannot be complete, because if it was, it would make, together with V, a k delta plus 1. Right? V has delta neighbors. If it doesn't have delta neighbors, then we're violating 1. So V has delta neighbors. If they make a complete subgraph, then together with V, we have a k delta plus 1. And in this subgraph alone, every vertex has degree delta. So they couldn't have any other vertices, any other neighbors. That would be the entire graph. And then we'd be in this case. Okay. So there exists a non-edge, say, between V1 and V2. Right? This is now not the same names as the Vi have here. Okay. Now, consider the path from V1 to V2 So that's a I can use white. No, yellow. Or let's say it is the same names, but the non-edge without loss of generality is between V1 and V2. That's a better way of phrasing it. So we'll consider this path C12. Oh no. And it has a vertex U incident with V1 that is not a neighbor of V, because this path has length bigger than 1, because this edge isn't there, right? So it's important that U is not a neighbor of V. And U is colored 2. Now, switch colors in C on C13 to get a new coloring C prime. So V1 has color 1. So this is C13. And let's flip colors between 1 and 3 on this path here. So V1 now has color 3. Then the next one here has color 1. That used to have color 3, now has color 1, and so on. So this used to be the 1-3 path, so here we have 1, 3, 1, 3. And these have now 3, 1, 3, 1. Okay. Now in C prime, in this new coloring, the vertex U lies in, well, it still lies in C21, because we didn't change the coloring C up here. So it's in C, let me give it a prime to indicate that we're referring to this, 1, 2. But U is also in C32, because this vertex has color 3. Its neighbor U has color 2 as before. So these are in the 3-2 component. But that means that that's a contradiction to 4. 4 says that these components are allowed to meet only in VI, and these are meeting in U, and U is not a neighbor, is not V2. Yeah. That's the end of the proof. Questions?